the parameters that are of interest in a channel model. So in general, these are the time dispersion parameters, which include mean delay. Basically, they're all about delay. Truly speaking, you can understand the delay in terms of simply by looking at what is the time at which the main signal or the line of sight signal arrived, and then what is the last non-line of sight arrived. So that is what is called the maximum delay. To express that in a more quantitatively using some metrics, you need to think about what is the mean access delay, RMS delay spread, and access delay spread. So spread is basically the maximum delay between the first line of sight, first signal, which is line of sight, and the last signal. Okay, and as we know, as Dr. Prakash also mentioning, there may be many paths, but not all of them are significant. Only certain paths are significant because they have higher received power. For example, if the received power is too small, like below the threshold or sensitivity of the receiver, then they don't mean much. So I hope you got the main idea. So let's look at these terms a little more clearly. And the other things are frequency related. Okay, and there is a beautiful connection or some sort of relationship between time and frequency things. You are going to see them in some of them in this presentation. So these are the parameters that we need to know, and then see whether we can use them in modeling the channel. Okay, that's not, in fact, that's a challenging point. So these things can be measured through some experiments or simulations. For example, delay spread. How do you measure? You can conduct an experiment, things like that we talked about before, like this. These are the three things that we can do to kind of come up with to measure this, to measure the delay spread, for example. Okay, the techniques are called like sounding techniques. The other option is, so by the way, these are real experiments. The other option is use a tool like the tool that I mentioned, Insight, to model some sort of a terrain, meaning that you're putting certain number of buildings or certain vehicles on the ground, creating here is a cell tower and here is a vehicle. So you are modeling the terrain, but your model is as good as your design, meaning that it will not reflect the reality. It's difficult to reflect the reality, and you don't know when you go to, like, for example, the center of the Warangal city or Hyderabad city. You cannot accurately depict in your simulation, but you do your best. And I'll tell you how I did in the right after wrapping up this. The other option is some of them are experimental, some of them are simulation, and then ultimately we need to end up with a theoretical model. Otherwise, it's not complete. So how do you translate the key thing that we are working on right now is, okay, these are the parameters of interest. Then how do you use these parameters to put in the channel model? That is the crux. Okay? And I've been working on it for 2 years, meaning that we are doing a bunch of experiments or a bunch of simulations. And as I told you, I'm talking to a professor. His name is David Metallock. He's in University of South Carolina University. He's an expert in this channel modeling field. So I'm getting his help, and together we are working on this. Okay, and because A-to-R channel models are oversimplified. For example, people use just a line of sight, free space. You don't need to do anything else. But that's what we are objecting. Our goal is to say, for example, at what height you can assume you have a free space. Let me explain that for a second. See, let's say this is about let's say 10 kilometers. Okay, I'm scaling this. The distance between the ground to the ceiling is about 10 kilometers. And then small drones, we know as of today, they will fly about 100 meters at a height of 100 meters. At 100 meters, may think about some distance like this table or this this podium. So at 100 feet, there will be buildings which may be 50 feet or 60 feet, or even it's possible, 50 feet building is possible, even 60 feet is also possible. So you will get a lot of reflections. When the drone is flying at 100 feet, you expect a lot of reflections. So obviously you cannot ignore multipath. Okay? And as of today, such models are being developed. There is no standard model for even for 100 feet. But when you go to the altitudes of air taxis, we are talking about 1 kilometer and more. And there was no need to model channels for drone to drone at that heights until now. There was no need. There was we didn't find use cases. But now that there are use cases, one idea is, let's assume free space loss. That means you are ignoring all these multipath things and all that. Can we do that? Can we afford to do that? Especially, you know that vehicle-to-vehicle communication is such an important aspect. Then you cannot ignore the multipath propagation. Okay? And not only that, before coming to the last point, what about then commercial flights? Commercial flights, we never had to worry about channel models, because what height they are doing, flying about 30,000 feet or 40,000 feet. So divide by 3, you convert into meters roughly. The rough estimate is 30,000 meters, like 3,000 kilometers. Okay, right? 30,000 feet divided by 3 is about 10 kilometers. So at that height, free space is okay. In fact, there are other problems. Dr. Prakash and myself were talking just now. Other issues are, if you want to come up with a channel model, first of all, it's not necessary, because I don't think today a pilot is talking to another pilot over the phone or even data. We don't create a network of all the commercial flying. There is no need. We talk to satellite, and through satellite you're talking to the ground control station. If you want to talk to another pilot, we talk through the ground control station, not directly. Number one. Number two is, the issue is, you can assume free line of sight or free space. That's not a problem, but more importantly, you need to look at absorption of signal through cloud and rain. Those are more important. Unfortunately, that such models are already developed. For example, what is the loss associated with rain or cloud or fog? Those were already available in ITU standards. So once again, we don't do that. It's typically atmospheric scientists, those guys do that. So my point is, it's a new area. Air-to-air channel model, new area. You cannot just blanketly say, let's use free space loss. That's exactly what we are objecting, okay, in my group. And it's a evolving thing. So what we want to do is, starting from, let's say 200 feet, 400 feet, 600, 800, at different heights, at different altitudes, what will be the channel from air to air? We're talking about when multiple drones are flying, what will be the channel model between two drones? Let's say one drone is here, another drone here. So we will look at the distance and then try to vary the distance between the transmitter and receiver. Okay? And then the altitude, change the altitudes. And even you assume, you oversimplify and say, they are flying at let's say 1 kilometer, and then they are the same height, and then the distance between transmitter and receiver is also you can vary. Even you do oversimplification, still it's not a done deal. It's still a lot of work has to be done. So the way we are approaching is, since we know these are the parameters that are of interest. Air turbulence, that also we are not done. In fact, we didn't even consider. We can account for losses because we have some thumb rules or empirical results or empirical models. But key thing is, using this knowledge from Rappaport's book, we want to see, can we develop a air-to-air channel model? Okay, that is a new research. All right. So look at, even for me, I never had to deal with this. I read this from papers, but I never had to work in meticulously. So the first thing is mean excess delay. It's like a mean. Basically, think like it's a spread. How I talked about What are we interested in? What is the spread from the time you get received the first signal to the last signal? What is the delay? So for that delay, see, look at this. There is a known metric, mean delay or mean access delay. Is something called first moment of the power delay profile, and that is it includes not only the, think about tau k is the delay. You are dividing total delay into segments, tau 1, 2, 3, and until the whatever until the end of the delay maximum delay. So starting from 0 to maximum delay, you are giving into segments, and each segment you are saying you are giving a name, tau 1, tau 2, tau 3, tau 4. Basically you are discretizing. It's a continuous thing, but you are discretizing. And then notice you are multiplying with the power. So what is the power you are talking about? What is power P of tau k? What is the power that the signal is received? For example, let's say you have let's say total number of values for k equal to 5. So you are saying, starting from the line of sight, what is the next null line of sight you are receiving at what time? That is tau 1. Okay. Next line of sight is at tau 2, is coming after tau 2. And what is the power associated with the second null line of sight? Okay, I hope you gather this. So yeah, it's like harmonics, but since this is all time domain, we are only looking at time domain. So it's exactly like that. Yeah, but you are discretizing, like, just like the way you discretize continuous frequency into discrete components, you are doing the same. But this is one term. The second is second moment. I think you can call that as RMS or standard deviation kind of thing. So these are like a first moment, this is a second moment. And maximum is, yeah, what's the maximum delay. So this is these are the things that you are extracting from the power delay profile. Okay, until now it is fine. The next question is, okay, how do I use this to model the channel? It is done for ground communications, but we are still working on it. Okay, so this is actually research in progress. We haven't published anything because we want to make sure that all the results are validated. It's not, they have to be meaningful, they have to be useful, and they have to be verified before we publish anything. Okay. Then there are beautiful concepts. I would like, if you spend some time, you will really benefit in the context of channel. One is something called coherence bandwidth. Follow this. You talked about delay. I think we spent a lot of time, right? We understood what is a delay spread. It's purely in time domain. We also learned about power delay profile. But let's look at the second thing. We say is the frequency range over which channel effects or channel parameters going to be the same. So what we are saying is, what is the frequency range of frequencies over which the channel behaves exactly the same way. Basically, you are looking for in terms of frequency in frequency axis or in terms of bandwidth, how are these channel characteristics are going to vary. So, and then you are saying, can we come up with a way of identifying the bandwidth over which the channel is going to behave exactly the same? Because otherwise, let's go further before we delve into this. So here, let's say, in other words, where the channel is considered flat over this bandwidth. So normally, channel is not going to be flat. Channel is going to vary over the frequency. Just like the way we call channel is going to vary over time. It's time variant. The same way over frequency also, it behaves different for different frequencies. So we are now asking, what is the bandwidth over which the channel behavior is going to be constant, and that is what we call flat. I hope you see the point. Okay, you need to understand the channel from both time and frequency, both sides. So for example, and this is this connection. We learned about delay spread just now, right? Now you don't have to do anything more. You can say, with some assumptions, So for example, he says if BC or coherence bandwidth is defined, sorry, there is a small typo here, defined as, ignore this, if BC is defined as the range of frequency over which the frequency correlation is above 0.9, that means you are giving a threshold. You should instead of asking a perfect matching, you are saying the channel is with plus or minus some delta, it behaves flat. Then the coherence bandwidth, so this coherence bandwidth is also by thumb rule. I didn't derive anything, okay, this is from the book, so it's not derived, it's like a general thumb rule. Is that if sigma tau is the RMS delay, then the coherence bandwidth is 1 over sigma t, sigma tau with some constant. This 50, I'm not deriving how this 50 came, this is more like a thumb rule. But in general, you can say the coherence bandwidth is inversely proportional to delay spread. That's the key thing that you need to know. Coherence bandwidth is inversely proportional. That is the key idea that you have to learn in both cases. So it depends on what is your threshold. So if the delay spread is longer, then this becomes small and vice versa. And please read these terms, try to understand more about, pick your Google or whatever and try to make sense of these terms. Not just as a definition. So I tell my students, you can read them, and but also you can try to understand the definition, but that's not enough. The more you try to understand the meaning of it, not the syntax, the semantics of it, then you will appreciate. For example, you can ask the question, why is there this relationship? Why is this inverse relationship? Okay. Then, the other thing is, so earlier we were talking about bandwidth coherence, right? In somehow you know that it's clearly related to frequency. Now the other term is coherence time. Doppler spread and coherence time are parameters that describe the time varying nature of the channel. So once again, this is another Doppler spread is, if you define FM as a Doppler shift. We talked about Doppler shift before, but here maximum Doppler shift is FM. Just like the way we analyze the signal in time domain, because of multipath your signal is coming, even though you are sending one signal or one impulse, you are getting multiple copies of that. Same way, because of vehicle in motion, you are seeing Doppler shift. But Doppler shift also is variable, it's not a fixed thing. Because if you look at the one of the previous diagrams, you will see that the distance is not going to be the constant, here. As you move, you are getting the path length is going to change. So when path length is changing, you get different Doppler shift. So the Doppler shift is not constant, it's varying as you are moving the vehicle. Even though velocity is constant, your path length is changing, and that path length, because of the path length, all this is going to change. In case of satellites also, actually, even though satellites are moving at a constant speed, probably that also is not correct, but let's assume satellites are moving with satellites. But then your relative distance, relative position, it has the line that you are connecting from the vehicle to the satellite will have a different slant. So which means that theta is going to change, the direction of what you call from the plane, from the horizon, from the ground, the angle is going to change. Because the angle is going to change, you are going to see a different distance, just like this way. So which means that your Doppler shift also is not constant. So that's the reason we are looking at what is the maximum Doppler shift. Yeah. So here I wrote just say coherence time. What is the meaning of coherence time? Time duration over which the channel impulse response is invariant, is fixed or flat. Basically, I think right term is what is the duration over which you can expect the channel response to be time invariant. Actually, in general, it's a time variant channel, but you're looking for what is the duration over which the response can be considered, assumed to be invariant. So, all these are factors that we need to consider when you are developing a channel model, okay. And that depends on the Doppler shift. You are seeing delay spread, Doppler shift, coherence time, coherence bandwidth. So, you saw the 4 parameters and they have a connection, relationship among them. Okay. We'll quickly wrap this up and then go into my research that I am going to present. So, everything is about small scale fading in this section, in this second half of the first lecture, and then here are the different types. Flat fading is when bandwidth of the signal is smaller compared to bandwidth of the channel, and delay spread is less than symbol period. See, this is the point, delay spread. If the delay spread is smaller than the symbol period, what do you mean by symbol period? The time it takes for you to transmit a symbol, one symbol. So, it is called flat fading if the delay spread, you understood, you know what is the delay spread, right? If the delay spread is smaller compared to symbol period, it is called flat fading. Otherwise, it is called frequency selective fading. In the same way, if we talked about coherence time, and coherence time is less than symbol period, we call fast fading. Otherwise, it is slow fading. So, it is not, I explained only the terms so far, okay. You still need to review this, understand the terms very clearly to understand, to learn the behavior or characteristic of the channel. For example, what do you mean by flat fading? What do you mean by time varying channel? These take some time. It's not just one lecture is not enough. If you have already, for example, typically if we give a lecture to students who are already thoroughly familiar with all these techniques, all these terms, then it is different. But I am actually making sure that you are learning something from this class. So, intentionally we are reviewing the basics. Okay. Now, having done all this, so now I am going to basically skip. I just wanted to make sure you understood these terms, and let us get into the research that I am currently working on. These slides are from the textbook, and I can also give it to you. Professor Sai Prakash is going to share with you. Yeah, these are partial results. In fact, we haven't finished, and we have been working on this for about at least 18 months to 2 years. And the professor I was referring to is Professor David Metalak, who is from University of South Carolina, an expert in channel modeling. And in fact, my understanding is that his paper on air to ground channel model received so many citations, and I think that brought him, made him that was the reason, that was the I think it is the reason why what he got his fellowship. He became an IEEE fellow, and people who are recognized as IEEE fellows, they have done something fundamental, and they received it. There are a lot of citations, and the work has become so valuable. Okay, so keep that in down the lane. If you do some work and a lot of people use it, then it will make your work very valuable. And this is my master's student who graduated recently. Yeah. So the reason we are studying air-to-air channel model is because we are expecting advanced air mobility services like air taxis and air ambulances in future, and we should have a clarity, we should have a clear picture of are we going to see clear line of sight or at what height, and then if you need to consider multipath propagation or multipath aspects, then how do you take them into account, and once you have a reasonable channel model, that will give us some ideas about what kind of path loss and what kind of how much communication range we can expect, and then also if there is multipath effect, then how do we address that, how do we deal with that using the known techniques, like for example, multiple input, multi-output, or maybe different new modulation techniques or new decoding techniques, new receiver design and all those. But in general, I think we just want to come up with a good, reasonable estimated channel model. So this is the outline. In fact, this is from her thesis. She presented her thesis and I took it to come up with this. These are all the applications. In fact, we don't have to get into in detail. There are many applications like this, and we kind of discussed this a few times in the class, in the previous classes. And these are the issues. And here, we already talked about in the previous half, but it's a quick summary. Fading means what? Fading is required because you want to have an estimate of channel gain, and more importantly, we want to see an impulse response representation of the channel. And so we need to take into account small scale fading and large scale fading. Large scale fading path loss that we already know, that is part of this. And shadowing refers to like big obstacles causing the signal not to pass through or obstructing the line of sight. So these are the large scale effects. Small scale effects we talked about. Time and in the time perspective, it's about delay spread. From a frequency point of view, it's Doppler spread. Both are necessary. And these are, when we talk about aeronautical communications or airborne networks, there are channels. These channels are important. Ground to air, air to ground. Maybe you can assume pretty much same. And then air to air is a new topic. Air to air is not addressed so much. And these are the things we need to consider. Antenna characteristics, propagation effects, multipath, environmental factors. The environment means how do you take into account like rain and cloud, dust in the air. In fact, we don't, as I said, we don't need to go to that basics, or we can always take existing models for understanding the impact of environment. And then more importantly, this is also critical. How do you validate? How do you start? How do you come up with this design? How do you model them? And where do you begin actually? Do you start with simulations or experiments? There are many ways to do that. You see, the reason I covered all those things are so that you are ready for this talk. Okay? Now, so what is the importance? Suppose you come up with channel model, so what? This is the same question you have to ask. Anytime you want to do, you're doing research, the first question is, why are you doing? In fact, that's what happened when I published my first paper. Conference paper is slightly easier, they accepted my first paper. In 6 months, started PhD, I published, I presented a conference paper, and it turned into a journal paper. The question was, who cares for this? So you have to explain why your problem is important, why someone cares, what do you expect, where do you want to see the use. So here are the reasons. With a channel model, it doesn't have to be perfect, but at least a reasonable channel model will allow us to figure out, to predict the performance. What do you mean by performance? I think when I was talking to some student, I specifically asking, what do you mean by performance? Okay, like I think a good example is people tell, oh, he's a great guy. So what do you mean by great? In what sense? Is a very tall guy, or is a tall person, or it communicates well? He or she communicates well. You need to go into basics and tell. So here, when you say, I want to improve the performance, you need to answer this question. In what context? What is the metric? Is a BER. So for everything you want to measure, you have to have a metric. Then other things are, this is a link performance. So link performance typically BER. BER is a good thing. Anytime you want to say what's the performance of a communication, this is one of the things that you do. Then throughput and latency. Throughput is data rate, and latency is the delay, round trip delay, for example. So for a good example is, if you are working with the geo satellites, your round trip time is large. And suppose say you are sending a message to Mars, then what's the round trip time? Like 10 minutes, I think. Huh? Say again? 28. Maybe round trip time, right? Yeah. So very good. You looks like you're tracking that. So I remember it's about roughly about 10 minutes for each way. Okay. So when the reason I was told you, right, I was working on a small project, and then say if you want to send a message and on the rover to the rover, and then there is a ditch in front of it, you have to give enough notice for it so that it doesn't fall, at least 10 minutes or 14 minutes. So latency is important, but for LEO satellites we are good. This round trip time is not bad at all. You can have a LEO satellite based voice communication, and latency is reasonable. And the third is, the other is a model, a theoretical model or even empirical model will help us to reduce the actual measurements. But ultimately at some point measurements are also important. You cannot come up with only theory. To validate it, you need to do some real experiments. But how many experiments you do? Like for example, in the simulations, you can say, oh, I want to keep the transmitter and receiver at, let's say, 1 kilometer, and then change the distance from 100 meters, 200 meters up to 2 kilometers. But how many experiments you can do? It's costly. But we need to do at some point. And then maybe one idea is, what we do is, whenever we do the experiments, we post all the data and make it available to public. There are such platforms. IEEE data port is one thing, and there even NIST. If you suppose want some data, then you can connect with some standard bodies, and they will provide the data for you. Okay, I will go a little quickly. So these are the three models, and ray tracing is the one we are using because we have a tool called Insight, and there are other things. You can conduct experiments. You can use ask machine learning to generate the data for you, right? And then ray tracing is something that we are using. And what kind of things you have to set up? Remember, resolve simulation, right? So look at this. Now you will be able to appreciate all these things. Where do you place the transmitter and receiver? I was showing you here a transmitter and receiver here, but that's exactly what. Distance, altitudes, and what kind of paths? Line of sight and non-line of sight. But how do you know line of sight? It depends on where do you place the buildings, okay, and the altitude of the buildings. And more importantly, when we were doing all this, and then I was talking to Professor Metalak, and then he asked me, what about material? Your permittivity or when you reflect the signal, you have to consider the permittivity of the material. See how meticulous you have to manipulate. You have to plan. But this is how to develop a channel model. All these things have to be done. As I said, we already spent a year or more than a year, and here is now comes the crux. Here is the transmitter, the geometry of line of sight. And where is this coming from? From textbook. We didn't invent anything. Okay, you put a building and say, let's start with one. Then you put one more, and then see one more. And change the material of the building, concrete or something else, right? And then my student, without even by herself, she put a bird here. She said, why not an obstacle in the airspace? So initially we didn't. I didn't think about, but she herself, my student, her name is Sudeshna. She put this and said she also considered the physics of reflections and refractions. It could be another vehicle. So what exactly happened was, when we were sending this data for the professor for validation, just asking for input, he was telling after 800 meters or so, you shouldn't be seeing any reflections. But then we told him, I was looking at the data and see where are these reflections coming from. You're not supposed to see reflections at a very high altitude. Those reflections are coming from some other obstacle that she put in the simulation. Okay, so all these are clear, right? There's nothing. But look at the parameters. So you need to, if you see, you have to be very precise. And when especially those students who are new to research, you're just starting your research career, you need to be, look at the textbook. For example, if you look at the Rappaport book, you will see all these parameters in some sense or other. Or look at some other paper. See what parameters they are configuring. Scenario, urban, simulation frequency, obviously you need to know. bandwidth. And what earlier we were talking about, it could be a pulse or impulse, or it could be a sine signal. And in the tool, actually, you can configure all this simulation area, and all these have to be carefully done. Height, total height is 3 kilometers. Transmit power is 30 dBm. You can calculate in terms of watt. And receiver threshold is -109. What does it mean? Notice the units. Okay, what do you mean by receiver threshold? Receiver threshold is if it is below this, then you can ignore the line, especially for the null line of sights. And antenna type, you could give omnidirectional. That means gain is 1, and then polarization is this is also an important thing. In fact, vertical and horizontal. Vertical means your signal is traveling, wave propagation or wave front is going in one direction, or if it is horizontal, there are two polarizations anyway. It could be angular also, but you need to define this. And these are, look at the, if you want to look at the textbook or Google, and you will see that when you see a beam like a radiation pattern, and you are looking for half power beam is beam width in terms of angle. Okay, in terms of angle, what you are configuring this. So what does it mean? After 90 degrees, your maximum power is going to be reduced to it becomes half. That's the half power. Beam is the angular angle at which, after 90 degrees. If you assume at 0 it is maximum, at 90 degrees is going to be half power. Same thing with there is also called null beam width. Gain, this is I think this is antenna gain, dBi is. So look at each of those parameters and learn about all this, the meanings of all this. And you are supposed to configure, especially you buy a tool. If you have a tool, you are supposed to configure. And then look at, this is what the student actually designed. She kept bunch of buildings, and X is a transmitter, Y is a receiver, and then she put some obstacles, something like this. These are all it's actually 3-dimensional. Okay, so let me show you. Here is the little more clarity. These are at different heights. So look at them. What's the maximum height? 800 meters. So she is considering buildings of height 800 meters. Well, it's actually the building heights are only 300 meters, but the obstacle heights are 800 meters. That means obstacle means they are flying objects. They can be anywhere, like birds and other aircraft. But the highest building is 300 meters. So this is the kind of shape that she has given. There is two obstacles, right? One is at 800, another is at 730. X is the transmitter and Y is the receiver. So this is a terrain model. It is easy to do. Once you know how to use the tool, this can be done in the simulation. But key thing is, set up the configuration and then start doing the experiments. You can measure, you can get line of sight, non-line of sight, how many non-line of sights are there. All this is done by the tool. So it uses this to figure out how many, depending on where you kept the transmitter and receiver, it gives you all the reflected components or non-line of sight paths. And then it gives you all those power delay profile, delay spread, RMS delay, all those things. I think, let's see. So one more thing is, you can make, to make it more interesting, how do you define, how do you figure out where to put the buildings, or what should be the heights of the building? And she actually considered a PDF of, she used this distribution to compute building heights. So how do you know this? How do you do this? You can, I think, look at the data. Based on the data, empirically, she found that in urban setting, again there is a difference. So that's where you have to do a lot of literature. The question was, our collaborator asked, put some buildings at different heights, but you want to know how should I design put the height? How do I choose? So one is you can put randomly. The other option is look at a good reference and see. She says this is there's a probability density for heights. So it means how do they do? From a statistical sense, you go to, for example, Warangal and some center of the city, and then look at find out that you can't do on your own. There will be some data available. So what are the heights of different buildings? And then from there, you can come up with your distribution, and this is the distribution she's showing. Okay. So now, use this distribution to pick some random samples. See, sometimes you can make the problem more interesting, by doing some studies. So that's how these numbers are coming. These are not totally random. They are random numbers, but they're not totally random. She didn't make it up. She uses a distribution to pick the numbers. Yeah, what you're saying is, depending on the height, you see the reflected component. The lower the height, probably you'll get longer paths. Here are the things that we already learned. Free space path loss, and that will be the baseline. Free space path loss is the baseline. This for the free space path loss applicable to line of sight. Obviously, this is nothing new. Clearly, so what you are seeing here is, this is the free space path loss from what's the distance between transmitter and receiver, and you are plotting the path loss. And this is for non-line of sight. This is for both. Of course, they have to match. Then they are matching. Even the tool also has some physics model to build the simulation. So this has to match. Like free space path loss and line of sight will be the same. So what happened here? She actually did a bunch of experiments. If the transmitter and receiver are the same height is 800 meters. She actually went up to 800 meters, I think, totally. Okay, ignore that. Basically, height is constant. This height is constant, but then distance between transmitter and receiver is varying from 1 kilometer to 3 kilometers. And then she obtained, through the simulation, she got all those line of sight and non-line of sight components, and then this is the average. You get a lot of non-line of sight, but only one line of sight. And obviously, these two have to match. Make sense? At least reasonable, right? You may not be able to understand everything, but reasonably, at least to some extent, how she's only plotting the path loss related to line of sight and whole lot of non-line of sight. And these are the expressions for delay spread. Received power actually, in this case, even though she didn't mention it, is the received power of each path. Because transmit power is always the same. There is only one signal, one sinusoidal signal that is sent. The received power varies. Transmit power doesn't vary. Okay, the time of arrival. So P sub P is the received power for n paths, and Tp is the time of arrival. Like each non-line of sight will be received at different times, and then she computing mean arrival time, and here is the RMS delay spread. We learned about delay spread before. We learned about RMS delay spread. Here is practically we are measuring. Okay, now it makes sense, right? If I showed this in the first slide or first talk, you won't understand what we are talking about. That's the reason I covered the basics first. And then you can see, look at this, at different altitudes, she went all the way from altitudes of what? Altitudes of the transmitter and receiver. They are exactly the same height. She didn't change the heights of transmitter and receiver. But this, you have to start with a simple model first, and then RMS delay spread is reducing. So the question comes, where is this normally supposed to be like monotonously decreasing? So when you see something like this, you have to ask. We have to ask her, or the researcher has to. Why is this delay? Why is this? So potentially probably we are, our reasoning is, you can't throw it out and say it's random. No, there is a reason why is this, because you're doing averages. There's something called law of large numbers. The more experiments you do, you're supposed to get a good distribution. So, in fact, yeah. So point is, this number is coming because there are obstacles in the air at some heights. So it's something to do with the obstacle that she introduced. So what we are going to do going forward is just remove all the obstacles in the air, see how it works, and then I asked my collaborator, should we even consider we considered obstacles. So he was expecting, he was not thinking about adding these obstacles in the airspace, but when I mentioned, okay, this potentially we want to, potentially you will see some other aircraft, some other obstacles, so you cannot not assume, you cannot drop them from the simulations. So he said agreed, he agreed, and then we are working on that now. So what she is saying is, at some point it will be 0, meaning that, what do you mean by that? When you say RMS delay, at some point the power is going to be 0. What does it mean? It means that you're only getting line of sight, nothing else. When the delay comes when you are seeing non-line of sight. So then, okay. Yeah. So there are some, these also supposed to be like a kind of a monotonously decreasing, and we are getting these ups and downs because of the obstacles. That's our guess. We don't know yet. So as I said, it's still in work in progress. So if you change the building heights, then you get a different results. If you change the building materials, you're going to see a different height. If you change the building material, you're going to see different results. So we want to collect all this, and then look at all these results we got. And ultimately, the goal is to use these experimental results to build a theoretical model. Okay, we are still working on it. Okay, so I think I'll stop here. She did a lot of experiments. And if you use directional antenna, what happens? And if you think about all these options are there in the tool, so but we have to come up with a little more details about the antenna parameters. If it's a directional antenna, then you have to set up all these parameters. MIMO. If you use multiple antennas, then okay. So basically, this research is about this presentation or this lecture is about how do we build, how do we develop a empirical air-to-air channel model. And the key things are understanding delay spread, power delay profile, path loss, and then those are the key things that we need to understand conceptually, theoretically, and also practically. Then I think we can develop such models. All right, I'll stop here. Any questions before we wrap up for today's lecture?
You said about the materials affecting the signal.
Mm-hmm.
So even if the buildings are of the same material,
Mm-hmm.
the surface, like the roughness of the surface would either reflect or scatter the signal.
That's also there, yeah. That's also there. You remember the scattering that we talked about. It depends on the. It's difficult to capture all the finer phenomena, So in general, in this case, we are only considering the reflections only. So it's not considered. And one thing is probably, yeah. The question you would ask is, what happens after scattering? Are you receiving that scattered signal back to the receiver? In this case, probably it's not. So you can ignore in that sense. So first of all, understanding all these different physics aspects is important. But then see what are applicable for this. Okay, if the scattered signal is going to travel that long, then you have to model that. But notice that since we don't know what exactly are the buildings, building materials, and all those things are only some high-level assumptions. So it is sufficient if we capture the the significant things and ignore the. But even you model, then there's something called overfitting, and you try to overfit, then it doesn't generalize. In machine learning, there is that we use the term overfitting. Don't try to, if you don't, we shouldn't try to overfit for one particular data. But if you do that, it will fail in the other cases. Okay. But the good point, you're right. That it is true. Surface characteristics will also affect. But given that reflected path is the scattered component is not going all the way to the airplane, we are okay to drop that. But a very good point. Anything else? Oh, well, for now, so remember, the fact that you are trying to looking at drone to drone communication, you are only looking at line of sight. Okay, line of sight is because of reflections, but it's not about going beyond visual line of sight. We are only looking at like a simple scenario, like I'm using this door because I don't want laser light to go to your eyes. So you are assuming that there is one vehicle here and there is one vehicle here. Okay, the distance that is should be reasonable enough reasonable enough in the context of one single hop. Okay, the distance is changed. If you change the distance, if you vary the distance from 100 meters to 2 kilometers, what does it mean? You are looking at a scenario where the communication range is varying from 100 meters to 1 kilometer or 2 kilometers. So, in fact, that's another thing one of my collaborators mentioned. We wanted a model where you can change the communication range. But to answer your question, we are saying that we are saying that it's only one line of sight, just one link, one communication link. That's it. Yeah, if you can increase the one hop distance, that depends on the transmit power. Okay, for example, if you in one experiment, we're trying to see, how come the range is so small? All we had to do is increase the power. So, but of course, it has to be within the regulations. I'm not sure whether we. Yeah, right.
Communication technology, right? There is a maximum limit for technology, but I can use a simple power where you like it. Even in case of static, the total power is constant. The static signal has taken 10 pass divided by 10. Right? Yeah. And it takes 20 scattered signals divided by 20. So it will not reach to the, so it can contribute for that. Whereas if you take terrestrial network, even a post, light post, we scatter the signal and that is sufficient to enter into your house. Right?
So look at these papers. This is the paper I was talking about. This paper got very well recognized. It got a lot of people actually used it. Air to ground propagation channel model. That's exactly I'm trying to work with him to come to build this air to air channel model. And then look at, there is one paper, air to air channel. There are some effort, but these are assuming you're only looking at 100 feet or 200 feet. Yeah. This is my lecture. Where is this? Here. From North Carolina State University. Yeah, he graduated from Florida. You know him? Who? Okay, yeah, he's from here. Yeah. He is well known. Yeah, he wrote lots of papers actually. Georgia Tech, yeah. But the nice thing is they're all kind of new area. It's fun to work in a new area. But at the same time, you have to be careful. If you do well, papers will be read. Otherwise, say if you don't do good job, nobody cares for it. They're put in the dustbin. But so we have to do a good job. At the same time, make sure that it's consistent with the known results and all that. It takes some time. Okay? All right, wonderful. Have a wonderful rest of the day. So we are done for this. So, yeah, yep, we're done for. Yeah.